is a great lesson for me here to honestly in connection with the international portion or statistical model examinations. We have a very great personalities with us for this workshop. All of you know Professor Balakrishnan, uh, first speaker of this workshop. We gave English personalities. In fact, before that, I shall give you why statistics. Or there are three, like Mahavar language. That's our distributions. Theory, the discrete distributions, mechanical distribution, only one word means. Our library, only different words. That's it. I, in fact, from my own came to know that there's a back uh, dots and points. Validation. Validation. That's it. That is all the people university departments, whether statistics or related subjects, throughout. And we are in G itself is a so we have always is always encouragement in this encouragements and this is fun. So we are very lucky to have people support. Uh, and also for this workshop, in fact, the initiated there yesterday, in night at 7:30, 7:30, 8:30, there was a small social lecture, one lectures by it's a data engineer from US. I hope some of you already entered that. So Prabhat Chaudhary is from ISI New Delhi. He's the chair of the unit, statistics, planning and economics. So, madam, your head of the unit is also will come over with donors after times. But before the lecture will come over, please begin this. She's also a professor in Delhi. And Professor Kishore Majumdar is also professor of chair of the Department of Computer Science on ISI Bank. He already planned to come over here. He is in fact a wheelchair person. So he planned when we moved from here to by his own car with two assistants, driver and another assistant person. But at last minute, some medical and technical issues come either is traveling. So he missed to Michigan. But he joined, he will then stop by today after. So we are very happy to have great respect, especially to that. And I hope we have a very good uh, workshop on statistic model language. And tomorrow, we have the international conference here at Kerala University. So this time we started such things with in collaboration with the visiting student. Because I have a very very deep desire to make this department as a research. So how to make? So how to make our active faculties and other students. So I hope in the near future we have it will become like research. And we can collaborate on research like this and we will make support arrangements. With a great pleasure. I'm not an expert in questions now, but we are waiting here. Important. So, with these few words, take me to conclude my advice and with the one questions. Thank you. Thank you. Thank you.
Thank you, sir. It's now my privilege to invite our distinguished guest, Kavakar and Balakrishnan, distinguished Professor, McMaster University, Canada, to formally inaugurate WSD 2023 and address the gathering.
Thank you very much for inviting me for this workshop. Can you all hear me? Then I don't need a microphone. I give lectures for more than 500 students at a time. So I don't use a microphone. Here there are about 50, so I don't need a microphone. It's a great pleasure to come. Uh, Dr. Satish Kumar and I go way a long back. I have been coming to his conferences in Kariyavatam campus. I always enjoy my visits. And this time it is special because I have a close friend in McMaster University, uh, Parmeshwaran Nayak, with whom I work. He's a medical doctor. And his wife's cousin is here. So it's a double pleasure. When I go back, I will tell you. So workshops like this are very important because you get exposed to different subjects like sampling theory, design of experiments, uh, regression analysis, and things like that. But in workshops, you learn other topics which you normally don't see in your courses. And these are topics where the current research is going on. So they are very important for you to be informed. And also, if you think what other research is going on other than what you learn, these type of seminars, conferences, workshops are very important. So I always make it a point when somebody invites, if it is for students, I without hesitation go. Because when I was a student, I fondly remember such workshops. So I hope you all find these workshops to be of interest and also probably help you to understand where the current research in statistics is. So thank you very much for coming, and I hope you stay for the day to listen to all the talks. Thank you. So it's with great privilege that I inaugurate this workshop, and it will be perfectly ideal if the principal would come and start the writing session. Okay. What was it? Yes. Yeah. You have to do. Good.
Thank you very much for your insightful elaborate to express our gratitude. I now declare Dr. Murthy from our final and for Good morning, all. As we come to the end of this inaugural session, it is my great pleasure to propose for prize forward. On behalf of the Department of Statistics, Government Tax College, Thiruvananthapuram, I extend my sincere thanks to our distinguished guest, Professor Dr. M. Balakrishnan sir, distinguished Professor of State University of Canada, for giving us the section WSA conference. Sir, we are truly honored by your presence and we look forward to learning from your insights. Thank you, sir. I sincerely thank our respected principal, Dr. Madhavi teacher, for presiding over this function and for her constant support and encouragement. Thank you, teacher. I would like to express sincere thanks to our uh, organizing secretary, Dr. Professor Satish sir, University of Kerala, whose hard work and their dedication have played a major role in making this event possible. Thank you, sir. Our heartfelt thanks to the head of the department, Professor Dr. Srijit B, for his warm welcome and dedicated leadership in organizing this event possible. Thank you. Srijit. Finally, not least, my sincere thanks to our department faculty members, other faculty members from other universities, other university colleges, research scholars, and this college, teaching and non-teaching staff, research scholars from this college and other colleges, students, and all for being with us today. Thank you all. And with the sincere gratitude to all, I conclude my vote of thanks. Thank you all. Have a wonderful day. Thank you. Thank you, ma'am. With this, we conclude the annual session. It's my privilege to invite our past resource person, study Professor Balakrishnan, distinguished Professor Macmahon University, Canada. He did MSc in Statistics, University of Madras in India, PhD in Statistics, IIT Canada, elected member of International Statistical Institute in 1992, fellow of American Statistical Association in 1992, fellow of Turkish Statistical Association in 2000, elected honorary member of Greek Statistical Love Common Award winner awarded by Asian Statistics in 2008. MacArthur Student Humanities Award why mission? Three for the faculty of science, one for the faculty of engineering, and one for arts and science program. Member of Indian Statistical Association, Institute of Mathematical Statistical Society of Canada, American Society of Quality Control, International Indian Statistical Association. Professor Balakrishnan, International
There are two findings. Accreditation talk and there is
Statistical application and have
correct.
as
The power for insight
we are
you can make it full screen. That's the second talk, yeah. Okay. Second talk. Yes, yes. Doesn't work. Connect it there. Okay, you can put it. Yeah, okay. I think I think it's okay. No, it's not working. Ah, it's okay. No, it's not working. Once you close it, doesn't work. I think so. Something is kind of. Now it works. I think that has to be over. Thanks. Thank you.
ഒന്നാം FIOGP സംസ്ഥാനതല ഉദ്ഘാടനം അല്പസമയത്തിനകം ആരംഭിക്കുന്നതാണ്. എല്ലാ അധ്യാപകരും അനധ്യാപകരും ഒന്നാം വർഷ വിദ്യാർത്ഥികളും കോളേജ് ഓഡിറ്റോറിയത്തിൽ ചേർന്ന് അറിയിക്കും. അറിയിപ്പ് ഒന്നാം വർഷ FIOGP സംസ്ഥാനതല ഉദ്ഘാടനം കോളേജ് ഓഡിറ്റോറിയത്തിൽ വെച്ച് അല്പസമയത്തിനുള്ളിൽ ആരംഭിക്കുന്നതാണ്. എല്ലാ അധ്യാപകരും അനധ്യാപകരും ഒന്നാം വർഷ വിദ്യാർത്ഥികളും കോളേജ് ചേർന്ന് അറിയിക്കും.
Is it finished? Oh, okay. Okay, thank you. Um, when Dr. Satish Kumar asked me to choose a topic, I chose this topic for the workshop. I have two talks, and I want to explain what this problem is about. A lot of people work on reliability theory, and degradation is also a concept of reliability. In reliability analysis, people usually treat lifetime data. Lifetime data in reliability analysis is nothing but you have these bulbs. You want to know how long these bulbs will last. So, what do? You don't know, it's a random lifetime. This bulb may fail before that, that one may fail before that. So, what do? In an industrial setting, you use these bulbs, put them on test, see how long it takes before they fail. So you collect data. Suppose I start with 50 bulbs. I test them. One fails in 136 hours, another one fails in 217 hours, etc. You collect the data, then you think about what will be a good lifetime model. Lifetime models are nothing but distribution, gamma distribution, Bible distribution, log normal distribution, etc. There are hundreds of distributions. So, what you do is you assume a distribution, then you verify whether that distributional assumption is reasonable for the data that you have observed or not. Remember, God only facilitates you to get the data. God doesn't tell you what the model is. The model we have to decide. And you can assume any model you want, but you have to assume the model that is consonant with the data. That means it's reasonable with the data. You use goodness of fit test, model validation tests, etc. Then you say, oh, for this data, yeah, gamma distribution is appropriate. And then gamma distribution has properties. You use them to predict. This is what is the warranty problem. So the manufacturer say, we give you guarantee on an average, these bulbs will last for 780 hours, etc. So this was the reliability problem and reliability analysis people worked on for many years. The reliability theory came into existence around 1940s, 1930s. So there are many books, many papers published, encyclopedic articles, etc. But the type of data I'm going to talk about is slightly different. This type of reliability data is called degradation data. Degradation means when you use the product, a good example is the projector light you have. The projector light need not fail for it to fail. What happens is as you keep using the projector's brightness, the light brightness will keep decreasing because you are using up the lights. And as the brightness keeps decreasing further and further, there will come a point when the brightness is so low, it's equivalent to failure. And that is what is called the threshold. So many data that you see are like that. You go to your mother's house, she has a grinder, and the grinder does not fail all of a sudden, but you notice she will say, oh, I used to make togel, it doesn't make it very well now because it doesn't grind properly. And what that means is the motor may have lost its juice or its power, and that decreases over its usage. And the reliability of a grinder is measured by the million revolutions it goes through. So, as the number of revolutions increase, the motor becomes less and less efficient. There will come a time when your mother will tell you this grinder has to be thrown out because it doesn't grind it. So there is no toggle for you. So they have to change. And this is what is the crux of the problem of degradation. And you can see this in many products. For example, you have a car, you drive, it has a battery. And the car battery, you keep using, the battery is not permanent. What happens is it keeps decreasing in its capacity, in its power. Then there will come a time when the mechanic will say, this does not have enough power anymore, you need to change the battery. And that the failure is a different mechanism. The failure is it has come to a point where it's not reliable anymore. And that's what is called degradation. So, at this topic, I started working because I went to Taiwan in 2007 or 2008, I forget. There was a professor there of industrial engineering, and this is one of the famous universities in the world called National Tsinghua University. And there was a professor by name Chen. He came and told me that I have a data. I want to analyze these data, but I don't know how to go about doing it. So he had a bright PhD student. Its name was Chai. It's like Chi, but the spelling is different. Chai. And Chai was his PhD student. So I took him as my student and we started developing the theory. So since then, I think I have published about 60 or 70 papers on this topic, and we also have a book on degradation model. So I'm going to explain how to model this phenomenon of degradation. because it's not like a failure time data that you normally see. Okay, that's the two guys. Professor Cheng is a professor at Tsinghua University, and it is his student, Chichuan Tsai, and he was my PhD student as well, and he is also in Tsinghua University in Taiwan. And National Tsinghua University is a high-ranked Q50 university. Okay, I'm going to give you an outline first, and I will skip this literature review. It's not important for the talk, but I will start with the background of the study on the degradation. Then, after I give the background, I will explain how the degradation model works. And you will notice that it uses some principles from some of the courses that you have taken, like distribution theory, inference, but the model is different because it's a stochastic process. So I have to motivate the model. Then, once you develop a model, next thing you have to do is to fit it to the data. So, statistical inference. I will talk about statistical inference. Then I will do the analysis and I will talk about optimal test plan. And the optimal test plan is if you are working in an industry, they want you to test and pass some judgment. They give you a budget and you have to do the test within that budget. How do you develop a test strategy? That's called an optimal test plan. And the other thing that you should do, always consider, is model misspecification. Like I said before, when you do the test, the God allows you to see the data, but God doesn't tell you what the model is. You assume a model. What if that model is not correct? Assume a data comes from normal distribution. If the normal distribution is not correct, what happens to your procedure? How to assess its effect? And this goes to information theory. And I will talk about information theory and its connection to model misspecification, and then I will conclude. Um, my time is till 11 o'clock. Yeah, because okay, and then I can do the second. I have another talk in which I generalize this model. This is a univariate model, and how do you do if you have degradation in two characteristics or more? Then you have a multivariate degradation process. So I will also talk about that in the second half. The two talks are here. Okay. Now, first you have to know what statistically we mean by different words. These are English words. They have a statistical connotation. First one means quality. People often say this unit is of quality. It doesn't mean it's of high quality. It just means it is ready to use. So when somebody says, "Oh, I have this battery, it is of quality," that means you can take it, put it in, and use. But that doesn't mean it is good. It just is ready for use. What is good is reliability. Reliability means it has a long-term quality. So if somebody comes and says, "I have a reliable battery in for my car," then I am interested because that may last for 5 years, 6 years, etc. So the difference between quality and reliability is quality means it's fit for use. Reliability means it has a long-term quality. Then the lifetime assessment for highly reliable products. Suppose the products are highly reliable, how to test them? What do manufacturers do? For example, you have, let us say, a refrigerator in the house. Refrigerators can last for 25, 30 years. So you cannot go to an industry and say, "Let me plug in the refrigerators, test how long it takes to fail." You will retire before they fail. So you cannot collect data. They are highly reliable products. So how do you test these highly reliable products? And this is an important question, which is answered by accelerated life testing. So I will talk about that. So, how to construct an efficient test plan in such a way that you can get timely information on products reliability to the customers. This decision problem strongly depends on the pattern of reliability data. what type of reliability data you have. So, I'm going to give you little introduction about statistical lifetime models. Eh, By the way, these statistical lifetime models, I get a lot of PhD students. I tell them it's a reflection of my life because the type of data that I'm going to show you just comes from my life. Complete data is what I started with in 1970. 1970, you look at any reliability life testing publication in the journal, they will say, here are the lifetimes, n units under test, n lifetimes I got, the distribution is log normal, how do you estimate the parameters? These come from 1970. Look at this data here. You see, I start the observation at origin, call it as time zero, and I have 10 units here or 12 units I test. The first unit fails at this time. You call that as T1. Second unit fails at this time. You call it as T2, etc. And you have about T10. So you have 10 lifetimes. Maybe some of these lifetimes may be long. This one may have taken 3.5 years. Some others may have failed early. So you have 10 lifetimes. What you want to do is estimate what will be the average lifetime for a future unit. So in 1970s, when I was an undergraduate student, this is a common type of data. And we were taught this how to fit. We were explained the method of moments, maximum likelihood estimation, etc. for this data. 1970, I was an undergraduate student before you were all born. Here comes next, 1980s, census data. And the census data is nothing but I do not have infinite lifetime to conduct a test. So the industry tells you that you can do this test for 1 year, not no more than 1 year. So you have a laboratory testing facility, you fix the scale, you put the units under test. Now, this unit failed before that 1 year period. Notice the second unit did not fail before 1 year. So, what do? You can, one way to do, naive way to do is to say, I throw out the data. But that would be a wrong thing to do because it gives you partial information, but not complete information. So you have a partial information that it did not fail in 1 year. It's a partial information. The other unit failed in 9 months, 10 months, etc. It's complete information. So in 1980s, this was a common form of data. If you look at the book of Wayne Nelson in Applied Life Data Analysis in 1982, he will explain this model, explain how to set up the likelihood function, how to estimate the parameters, etc. There is a problem of no failure data. Suppose here you fix 1 year and you take, for example, refrigerators and test them. And you will know that, for example, my mother had a refrigerator for 33 years. She passed away before the refrigerator. Some of these units are highly reliable. So what happens if you fix a 2 year period and no unit fails? This is called no failure data. And this is a strange scenario, but this happens often. For example, car batteries, they may even give you warranty for 4 years, but the battery can go for 8 or 9 years. So, what do you do in this situation? This is where what is called as ALT, accelerated life testing, came into picture. You see that accelerated life testing. ALT stands for accelerated life testing. What do? For example, if I have a car battery, I can identify what are the stress factors and I can increase the stress on the battery. For example, it may be related to the humidity in the air, it may be related to the temperature depending on the unit. What do? Here you see these are the stress levels. Yes, not is what is called as baseline stress condition. Whatever is the average temperature in Trivandrum is the baseline temperature. But I can increase the temperature in a laboratory, and that will be S1, S2. I can keep increasing the stress levels SM. You see here, I have assumed a model, but there is no cross. That means at the normal stress level, there is no failure. When I increase the stress level, for example, from the temperature of 30 to 40 degrees, then you see that a few units fail. Then I increase it to 50 degrees, etc. More and more failures occur. So, this is what is called as accelerated light testing. Why do we do this? Because this is the only way we can collect data. The data does appear on their own at the normal stress level. The normal stress level is the units are so reliable they won't fail. So you increase them. Then somebody can ask, so you have got more failures here, you have got less failures here, you have got no failure here. What do? Because I am interested only here. If you live in Trivandrum, you don't want to know what happens to the car battery at 60-degree temperature because there is no 60-degree temperature in Trivandrum. What's the point? But so what you need is a model that will connect the failures from different stress levels. And that's what is that model. This is a physical model. This is sometimes called as Arrhenius model, power law model, because these are thermodynamic principles. What happens if I increase the voltage, for example, on units, computers or laptops, or what happens if I increase the temperature, you have a power law model. So this model, you see, what it will do is it will take the data and then it will extrapolate it to the normal operating conditions. And this is based on physical principles. Now, what it does is if I know what the lifetimes are here, I want to know what is the mean lifetime at the normal operating condition. So you use the power law model to extrapolate the lifetime characteristics at the normal operating conditions. Go. Okay. Now I have a few things here. This is called remember, in degradation model, there is a quality characteristic. That's not the reliability. For example, if I think about batteries, the voltage it has is a quality characteristic. If the voltage decreases, the battery is like, for example, the quality characteristic will be the brightness, luminosity. How bright is it? It's a quality characteristic. If the brightness decreases to a certain level, then you consider it to be a failure. So it's called quality characteristic QC. It's related to reliability and it degrades over time. And then this is like a fatigue data. You see here, you start at time zero, there is no crack. In the crack appears on the surface. And the crack becomes used in airline industry because when the cracks appear on the surface, initially they won't care. For example, it may be 0.01 millimeters, but as the crack becomes bigger and bigger, they have to replace the unit. And this crack length is a quality characteristic. If the crack length becomes too large, then you consider the unit to have failed. This is what is called a degradation model. So, what do? You collect the degradation data at various time points. For example, if the aeroplane has covered 100,000 miles, they observe how big is the crack. If it covered 200,000 miles, how big is the crack, etc. And they collect the degradation data, then the unit is considered to have failed once it crosses a certain threshold. That's the threshold. The threshold is omega. Once the crack length exceeds omega, it's too dangerous to use this machine. So, the degradation until that time you can observe. Once it crosses the threshold level, you have to pull the plug on that unit. You cannot use it anymore. So, what is the lifetime you observe here? The lifetime is that particular vertical line. That's a T. How do I define T? the lifetime is infimum on the time scale where the first time the degradation at time t exceeds omega, the threshold level. And in distribution theory, this is what is called as first passage time distribution, FPT. First time the passage crosses a threshold. And what do you observe? I observe only t. So the model has the distribution that I have to assume is nothing to do with this degradation process. It is the model that I assume on this curve. You see this curve? That curve is the distribution I assume for my time t, which is the time to cross the threshold. So I observe this time to cross the threshold on different units. Then I have to ask, what is the percentile? If I want to know what is the 95th percentile, what is the mean time to failure? How long does it take before a future unit will cross a threshold? Mean residual life. Suppose it did not fail for 100,000 revolutions. When is it going to fail? After. Mean time to mean residual life, etc. All of these are things that we want to make inference on, but the data is based on this theme and how to model such a data. This was the question that was posed to me in 2008. We constructed a model. I will explain. Before this was 2008, before that, Doxam and Hoyland had a model. It's called Wiener degradation process. Does anybody know what Wiener is? Yes? Have you heard of the name Wiener? Norbert Wiener is a physicist who actually studied statistical physics. So the Wiener process came because he introduced this Brownian motion based model. It's called the Wiener process. So what is a Wiener degradation process? You look, oh, what happened? Oh, it came back. You look here, that the degradation increases, decreases, decreases, etc. It goes up and down. When does a degradation happen like that? For example, if you are sitting in a air conditioned room, the voltage, sometimes it goes up, sometimes it comes down. So it goes up and down. This up and down movement is called the Wiener process. Now, what is a model? You see here, time is in hours. That is a quality characteristic. And the quality characteristic may be, for example, the voltage. It goes up and down. The model assumes if I take two time points, I take the degradation at time point t1 and I take the degradation at time point t2, I take the difference, delta. Delta is L of T2 minus L of T1. So that's the increment. So that is the increment. At time t, t plus delta t. The increment follows a normal distribution with mean eta w delta t, whatever is the width, times some scale constant and the variance sigma squared delta t. So independently they follow a normal distribution, so they can go up and down. And here the normal distribution is what Wiener process assumes. Notice here there are two parameters, not just mu and sigma square. They are related to the time, drift in time. They have to be related because the increment that you give determines how much of degradation has changed. If you measure every hour instead of every day, the degradation may be little. So this parameter eta is called the drift constant. If eta is positive, the cloud of these curves will be pointing upwards. If it is negative, it will be pointing downwards. The parameter sigma is called the diffusion coefficient. Sigma determines how much of bump is there. So if sigma is small, all these will be very narrow. If sigma is large, there is violent variation between them. So that is why it is called the diffusion coefficient. So But the problem is, this is not useful for the luminosity or the crack. Remember that I gave two examples earlier, lamp and crack on a surface. They cannot go up and down. Once a crack of 5 centimeters or 5 millimeters is there, next time you measure the crack, it has to be at least 5. It cannot go down. So that tells you that a Wiener degradation process is not suitable for a monotone degradation. So that's what I mentioned here. A Wiener degradation process is not a strictly increasing degradation path because it goes up and down. So if your quality characteristic is a degradation characteristic which increases monotonically or decreases monotonically, this Wiener degradation process is not suitable. What do you do? How to construct a degradation path or a degradation model which would be monotone? That's the question. This is where the gamma degradation process comes. A gamma degradation process will have a monotone increasing pattern, and it is ideal for describing the degradation path of some specific products that display a monotone behavior. For example, crack growth. We know the crack growth cannot decrease, or the level of luminosity. Luminosity is a monotone decreasing pattern. It cannot increase all of a sudden. So, in these cases, you have to come up with a model similar to Wiener degradation process. And that's a gamma. Look at this here. You notice there are no ups and downs. They are always monotonically increasing. And this process has to be defined. And that's what I define. L of t is the measured degradation path for an individual unit at time t. What does the gamma degradation process do? You assume the increment delta L of t, which is the degradation at a time unit in the future, t plus delta t minus the present time L of t, they are independent, just like in the Wiener process. Except you now assume delta L of t has a gamma distribution. And the gamma distribution, as many of you know, has two parameters. One is a scale, one is a shape. And here, alpha is the scale, lambda as alpha is the shape, lambda is the scale. Lambda controls the amount of variability, alpha controls how the process increases, how fast or how slow it increases, and that changes with time, alpha delta t. So, this is one of the nice processes which has not been studied when I started in 2008. Now we have published more than 40 or 50 papers on this particular model, how to generalize it, how to make inference about it, how to test hypothesis, etc. So I'm going to skip the these are the two papers, doesn't it? We don't. Here is a motivating example. This is, by the way, a very nice book on reliability, statistical reliability of data. Maker and Escobar in 1998. It's a book in Johnson by John Wiley and Sons. Now, I want you to look at this picture because this is the data you get. The picture gives you the data. Now, you notice here, this is the percentage increase in operating current. There are high focused laser operating lathes, and these are high precision machining tools, laser tools. And the operating current is very important for the laser tools to operate very well. If the current increase every time you use it increases, but it cannot keep on increasing because once it crosses a 10% increase, then the unit is not safe to operate. The lathes are shut down. So the operating threshold is failure level is 10%. These are percentage increase in operating current. Once the operating current goes beyond 10%, the lathes are considered to be unsafe to use. So that is the failure level. What sort of data you have here? You notice here that this, oh, this is the other one I'm using. Okay. Uh, I use the green. I'm colorblind. I cannot see red. Uh, okay. So here is the failure level. And you see that the units start at time zero. Then at 500 hours, they observe what the current level increase is. At 1000 hours, 1500 hours, etc. Those are the times. And what is the failure level? 10%. That is my omega in my degradation model. And the laser tested units is 15 degradation processes here. So there were 15 laser units. Now, you cannot go back to the manufacturer and say 15 is too small, give me 50. Because each laser lathe machines will cost you several millions of dollars. So they have given you 15, you should be happy you got 15. How do you multiply the data? You multiply by the measurement frequency. Every 250 hours, you measure the degradation amount. Then you go to the next 250, next you go to the next 250, etc. The measurement number is 16. That means 16 times 250 is 4,000 hours. So your observation time is up to 4,000 hours. You see that? So this is and then he was explaining who is your household. If now I want to plan a future experiment, if now I want to plan a future experiment, suppose manufacturer says you have X amount of rupees or dollars and you